going to talk about the standard normal probability distribution. And this is where z-scores come into effect, or z-scores if you prefer. So, here's the example. Your midterm grades are in. You score an 84 in calculus. Congratulations. 93 in Spanish and 79 in AP Physics. Run downstairs to share your grades. This time comes for you to blurt out your results, and suddenly a barrage of questions begin running through your head. Which score will I share first? Which am I most proud of? Surely the 93 is best, right? Because 93 is greater than 84, greater than a 79. That's simple math. But the Spanish test was easier. Plus, your friend just sent you a text message saying she scored a 61 in calculus. AP Physics has challenged you all year, and your last test score was in the 50s, so the 79 was a major improvement. And how will you decide which score was your biggest triumph? What you need is a way to put the scores on the same scale. The solution to all of your problems lays within the standard normal distribution. A distribution that assigns scores based on performance relative to how others performed in the same population. So, I have a question. Has anybody had a class so far at George Brown where the instructor has created a standard normal distribution from grades in an evaluation that you've taken? What does that mean, Song? They did or they didn't? I have no idea. Okay. Anybody else? Any evaluation that they think was standardized? You don't think so? Okay. Well, since this is stats class, and since I'm teaching this, there's always a possibility. And what it does, the difference is, you're one class. So depending on how the class does, say everybody did poorly, I can adjust the grades to standardize them to make them relative to each other in the class, not to an absolute value. That's what standardization does. Okay, so I'm going to show you a video. It's a very long video. We're not going to watch the whole video, but just so you get the idea about what standardizing is. Whoops. Sorry, a little slow. Okay.
I'm enjoying making these concepts a little bit easier to understand for you. Here we're going to talk about something called the normal probability distribution, the normal distribution. I think I kind of hinted in the previous section that we're going to end up talking, or maybe it was in the first section, that we're going to end up talking about something called the normal distribution. I cannot stress enough how important the normal distribution is. There's some things that are kind of like cute to learn and understand, and then there's some things that are super important, and one of them is the normal probability distribution. Almost all the time when they...
I'm just going to stop him, because what I want to say is, yes, it's probably the most important concept that you will learn in statistics. Because what we want to do, or what you want to do, depending on what kind of data that you're getting, you want to standardize your distribution so it looks like a normal bell curve.
They take these presidential surveys of small samples, and then they try to extrapolate it. There's some sort of normal distribution involved. And, usually when you're trying to look at the way in which things are distributed in their length or their weight, the IQ distribution of people in the country, grades. I mean, there's so many examples. The normal probability distribution pops up everywhere. It's kind of ingrained into the fabric of world we live in, is sort of the way you think about it. So I'm going to outline what it is with a practical example, draw a picture. I'm not going to draw much on the board. It's mostly going to be a lecture. I'll draw a picture to show you what it looks like. And then we'll kind of compare and contrast it to what we learned in the last section. We also introduced to these probability distributions. So let's say you go to the supermarket and you pick a watermelon. Now there's a whole giant shelf of watermelon. Maybe there's a giant, fenced off area where they've got like 200 watermelons. And you randomly pick one. So you don't really look at it. You just close your eyes and you grab one. Right? Now you know that there are watermelons of all different in sizes. But you also know that watermelons can't be as big as a truck, right? And watermelons, unless they're baby watermelons, they're not going to be like as small as a ping pong ball. I'm not talking about babies. I'm talking about adult, mature watermelons that are in the grocery store, ready for you to pick. So what we call mature watermelons. Let's say you pick one of these guys at random, and then you get a tape measure and you measure its length from end to end along its longest direction, and you measure that length and you record that number, right? And let's say you go back and do that again and get a second watermelon, and then you get another watermelon, all randomly. Each time you do it randomly, you get a result that is basically its length. So you could say the random variable here that we care about is the length of the watermelon, because the experiment I'm doing every time is randomly grabbing a watermelon and measuring its length. The outcome of the experiment, which we're calling a random variable x, is how long that thing is. Now we know that we're never going to get, or almost never going to get the exact same length. Even if they look like they're pretty close, they're probably going to differ by a fraction of an inch or a very small amount. We also know that if we look at hundreds or thousands or maybe millions of watermelons, that there will be some trends. We're going to figure out that most of the watermelons are going to have an average length around a certain value, right? And we know that some watermelons are going to be a little bit bigger than that, and some watermelons are going to be a little bit smaller than that. But still, there'll be an average value, and most of the watermelons will cluster around that. Now, you may have the crazy watermelon that's giant compared to the average, and you may have also the crazy watermelon that's a puny little watermelon compared to the average. But still, there'll be an average value, much like grades in a room. There's an average value of the grades. Some kids are going to get hundreds, 95. Some kids are going to get 66s. There will be a average value. Getting back to our watermelon, if we want to represent the spread of these watermelons, or I should say maybe the probability of drawing a watermelon with a certain length, draw it in terms of what we call a normal distribution. We say that the lengths of these watermelons are normally distributed. So a problem in statistics, if you see something is normally distributed, you automatically know it's going to have the shape that I'm going to draw on the board. And so let me show you that right now. This is called the normal. And it has such a powerful name like normal because it's the one that's so common everywhere. The normal distribution. And in fact, it's a normal probability distribution, really it is. So let's go ahead and draw that. So here we have an axis here. All right. And I draw a vertical guy here. I'll do my best to draw, but I'm not a perfect artist here. Now, for our watermelon, we're going to say that the average length, if we took a sample, a million watermelons, million perfectly ripe, farm-fresh watermelons, let's just say the average of the length is 20 inches. 20 inches. So we'll put that there because it's 20 inches. Now, obviously, some watermelons are going to be bigger than that. It's going to be this direction. So I'll say this is the length in inches. Some watermelons will be longer than that, and some will be shorter than that. So we might have some that are 25 inches. We might have some that are 30 inches. And we also might have some that are 15 inches. We might have some that are 10 inches, and we may have some really dwarf watermelons that are even smaller, but most of them are going to be right at the average. That's what the average value is. So I'll put this is the average, or as we call the mean. We've been talking about the average value in statistics. We call that the mean of the population of watermelons in the world. Okay. So then we want to see what this looks like. The normal probability distribution looks something like this. It goes like this, and it does not touch the axis here. Notice that it comes down. It does not touch the axis, but it kind of goes like an S, like this. It gets closer and closer and closer to the axis. It never really touches it. And I'll do my best to be symmetric, but I'm probably not going to do a great job. This goes down like this. this goes down like this. So that's actually not a bad job. What this is supposed to show.
Okay, so this looks familiar, I hope, for everybody. That's your standard normal distribution, the bell curve. Okay, where if you look at, let's say, where he's got 15 to 25, that's where 68% of the total number of watermelons, their length, is within one standard deviation of the mean, which is 20 in this case.
Show you is a perfectly symmetrical distribution. I kind of screwed it up a little bit up there, but you get the basic idea. This goes up like this. So what you are looking at whenever you look at a normal distribution like this is here's the mean value of the length of the watermelon. So you can kind of think of this axis right here being sort of like the probability, right? The probability. So you can look at this and say, hey, what's the probability of getting a 20? Well, it seems to be a maximum. So by looking at that normal distribution, I can see that if I randomly draw a watermelon, I'm most likely going to get somewhere around 20. Now, as I get a little bit farther away from 20, I've still got a pretty high probability. But as I get farther and farther away from 20, the probability falls off as this bell curve. You may have heard of a bell curve. That's what it is. So when you see normal distribution or normally distributed or bell-shaped, bell curve, it's all referring to the same thing. It's all referring to this graph right here. You can see a few things about this. So this curve represents kind of like the probability of sort of selecting these different values, for lack of a better word. The highest probability is always going to happen around the mean because that's where most of your, by definition, if it's the mean value, then a large part of your population is going to be right around that value of the mean. So the probability of getting a watermelon right around this is pretty high. Anywhere right around the mean is pretty high. As you get farther from the mean, the probability gets lower and lower. Eventually, if you get so far away, this graph goes so close to the axis, the probability effectively becomes very close to zero. If I get 55 or 85 inches way down off the chart, probability is going to get super close to zero. All right, so that's the deal with statistics. If I get really far this way, less than 10 inches, let's say, probability is going to get really far to zero, close to zero. So there's a couple of things I want to make sure. I'm going to hit the bullet points here as we talk about this. So the first one's obvious. It's called the normal probability distribution. Number two, this is called continuous. I'm going to write that down. I'm going to say this is a continuous.
So again, this is the second point. This is continuous, and this is what we're talking about, the continuous distribution. So you can measure, and it can go from negative infinity, in this case in the bell curve, to positive infinity. Okay, but it never reaches either one. Okay, it gets very close to, but never reaches either negative infinity or positive infinity. Is there any questions about that? No? All right, we'll continue. Oh, sorry. No questions. All right.
Distribution. Notice, what is the difference between this and what we had on the board in the last lesson? Last lesson, the experiment was totally different. We threw coins. We only had certain kinds of results that could happen. 0 heads, 1 heads, 2 heads, or 3 heads. There was no in between. But with watermelons, we all know it's possible that it could be 10 or 15 or 20 or 25 or 35 inches, but they could also be any length in between. The possibility is there for a watermelon to have any number of lengths. So it's not discrete anymore. It's called continuous. And in real life, almost everything is a continuous probability distribution. It's going to look like this kind of curve, and that's why we study it so much in statistics. All right, number 3, the random variable x is the length of the watermelon. So that's what we call the random variable x. We already kind of said that. We do the experiment, pull the watermelon, random variable is what we're talking about here. We graph. The normal curve that we have on here is symmetric about this axis. I haven't drawn it perfectly symmetric, but if you were to hold a sheet of paper and kind of draw the other side, it should look absolutely symmetric on both sides. And it's bell-shaped. We talked about that. The number 5 here is extremely important. This graph is completely defined by the mean of the population of watermelons and the standard deviation of the length of those those watermelons. So I'm going to write that down here. So the normal distribution completely defined by the mean, which if you remember from volume 1, we talked a lot about the mean, the average length of these watermelons, and the standard deviation of the length of these watermelons. We represent that as lowercase sigma like that. What I'm trying to say is all of the normal distributions, they all look bell-shaped, but some of them are going to be fatter, some of them are going to be tall and skinnier, and so on. And also, they might be centered. The reason it's centered around 20 is because the average value, we're just saying in this particular example, is around 20. But I may have cantaloupes or something else. The average value may not be 20 for anything else. But we're looking at cucumbers. The average length of cucumbers might be more like 14 inches or something. So the shape and where it's placed is going to be completely defined by the mean, which is going to show you where the peak is, and the standard deviation, which is going to show you how fat this curve is.
Okay, so that's another important point. We've gone through this a little bit. So once you know what the mean and the standard deviation is, basically you are able to draw the curve. You can figure out where most of the data lies. It lies around the mean if it's a normal probability distribution.
We're going to get to a little bit more about how that works in the next section, but I want to just tell you that you pick a value of the mean and a value of the standard deviation, and you completely lock down what your bell curve looks like or what your normal distribution looks like.
Okay, I'm going to stop there and go back to the PowerPoint. Basically, that was a little bit of a review for you. Any questions about that? No? All right, good. All right. So continuing. So you've received different grades. We don't know whether the tests, and you already know. You may think some of the tests in here are hard. You may think some of the tests in your other courses are hard. And how do you compare them? The usual method is to standardize the data. Okay? You're making it a perfect bell curve. If you have an instructor who gives you really easy tests, and that happens all the time, and the class average is 90, there may be something not proper there because the tests are too easy. So you want to standardize it. And remember, when you're standardizing it, you're making the comparison with the rest of the class and not an absolute value. Okay? So in this case, in the example of the grades, you assume, perhaps a bit unreasonably, that all midterm scores were normally distributed. However, there are infinitely many normal distributions in the world, each one centered around its own average with its own standard deviation. For example, calculus midterms have an average of 73 with a standard deviation of 8. Spanish midterms have an average of 87 with a standard deviation of 6. Physics midterms had an average of 70 with a standard deviation of 15. So from this, who can tell me which was the hardest course? Anybody? Take a guess. You shouldn't have to guess. If you look at these numbers, tell me which one is the hardest course. Okay, and Song, why is physics the hardest course? From this data, what is it telling you? It has a lower average. What else? And a high deviation. Correct. It's more spread out. So, physics has an average of 70. The deviation is 15, which means if we add 70 to 15, we get 85. We subtract 15 from 70, we get 55. So everything that lies within one standard deviation is between 55 and 85. Correct? It's a very big range. That means not necessarily, but usually, John. You can't do that assumption for all data. Okay? But in this case, the average was the lowest of the three, and the standard deviation was the highest of the three. But if you add and subtract the standard deviation from the mean, you get the range of one standard deviation, one below and one above. It goes from 55 to 85, which is a very big range. Okay? So anybody who scored higher than that would have been in the second standard deviation above, and below that would be in the second standard deviation below. Okay? So when you have the data like this, and it gives you the mean and standard deviation, right away you should be able to identify, okay, you know what? Whatever you're grading, in this case grades, you can go, oh, you know what? The physics midterms were harder than the other two. And which one is the easiest of the three courses? Spanish, correct. Because it has an average of 87. The mean is 87. Standard deviation is 6. If we add 87 plus 6, we get 93. And 87 minus 6 is 81. Okay? That's a very high average. It can also tell you some characteristics. You can say, oh, you know what? The Spanish midterms were easier than the physics midterms. If there's any questions about that, does everybody understand that? So even when you know that information, you can make some generalizations about whatever you're measuring. In this case, it's courses. So when you compare across distributions, which is akin to comparing apples to oranges, you make an informed decision and you convert all the scores to the same scale. So if you've heard that saying, well, you can't compare apples to oranges. Well, yes, you can, depending on what you're measuring. You know, if you're measuring, you know, whatever, the width, the height, you know, the size of the circumference of an apple compared to an orange, you certainly can compare them. So you standardize the scores, converting them to standard normal distribution with a single mean and a single standard deviation. So the properties. And the standard normal distribution, commonly referred to as the Z distribution or Z distribution, is a special case of a normal distribution with the following properties. It has a mean of 0. It's always 0 when you have a standardized normal distribution. It always has a standard deviation of 1. The areas under the density curve can be found using a standard normal table. A score on the standard normal distribution is called a Z-score. It should be interpreted as the number of standard deviations on a data point above or below the mean. A positive Z-score indicates that a point is above the average, and a negative Z-score indicates a score below the average. And the standard normal distribution follows the empirical rule 68, 95, 99.7. Right? Everything within is 68%. One standard deviation above the mean is 95, and 99 is 2 standard deviations above. Okay? Sorry, 95 is 2 standard deviations, and 3 is 99.7. Okay? We covered this somewhat, and you should know it. And a Z-score is a numerical measurement of a value's relationship to the mean in a group of values. If a Z-score is 0, it represents the score identical to the mean score. Okay, so that's why it's always been said, if you have a standardized normal curve, the mean is always 0 and the standard deviation is always 1. Z-scores can be positive or negative, with a positive value indicating the score is above and negative score is below. And the positive and negative scores also reveal the number of standard deviations that a score is either above or below the mean. So breaking down the Z-scores, it reveals to statisticians and traders, if you're going to be involved in that, investing in stocks or bonds or funds or whatever you're going to be doing, whether a score is typical for a specified data set or if it is atypical, which means it does not follow the normal curve. In addition, the Z-score also makes it possible for analysts to adapt scores from various data sets to make scores that can be compared to one another accurately. Usability testing is one example of a real-life application of Z-scores. So the usability of some object, some utensil, whatever you want to measure, you can measure A versus B, apples versus oranges. So the Z-score is commonly known as the Altman Z-score. Edward Altman, a professor at NYU, developed and introduced the Z-score formula in the late 1960s as a solution to the time-consuming and somewhat confusing process investors had to undergo to determine how close to bankruptcy a company was. In reality, the Z-score formula Altman developed ended up providing investors with an idea of the overall financial health of the company. Any questions about the Z-score? No? All right, we'll continue. So, the Altman Z-score is the output of a credit strength test that helps gauge the likelihood of bankruptcy for a publicly traded manufacturing company. The Z-score is based on 5 key financial ratios that can be found and calculated from a company's annual 10K report. The calculation used to determine the Altman Z-score is as follows. Z-score equals 1.2a plus 1.4b plus 3.3c plus 0.6d plus 1.0e. And A is a working capital, B is retained earnings divided by total assets, C is earnings before interest and taxes divided by total assets. Nope. All right, sorry. And there we have the formula. Okay. So if you look, or you can look at the back of your text, it will have a table like this with a Z-score, okay? And these various values starting at 0.00, 0.01, 0.02, so on. The standard normal distribution is a normal distribution with a mean of 0, standard deviation of 1. It's also called the Z distribution. A Z value is the signed distance between a selected value, designated as large X, and a population mean, that's supposed to be a mu, divided by the population standard deviation sigma. The formula is Z equals X, whatever the value is that you found, minus the mean divided by standard deviation. That's how you determine a Z-score. And you can look on the table what the Z-score is. In this case, 0.4332 is in this area. Okay, and you know, if you look over here, the Z-score is 1.7. You already know it's above 1 standard deviation of the mean. So it's between 1 and 2 standard deviations. Any questions about that? About reading the table? No? All right. So Z in the slide is the Z-score in the table. This is the Z-score, okay, 1.5. Looking at this area under the curve. The area is based on this. 0.4332, the z-score is 0.5. In the formula, though, yes, sorry, it is. It's in the table here, okay? If you get a chance, look at the table at the back of the text. So here's an example. Weekly incomes of shift foremen in the glass industry follow the normal probability distribution with a mean of $1,000 and a standard deviation of $100. So the question is, what is the Z value for the income? Call it X. Of a foreman, yes, you get the table. You call it X of a foreman who earns $1,100 per week, or a foreman who earns $900 per week. So if we figure out the Z for X equals 1,100, here's the formula, 1,100. That's what's asked for. The mean is 1,000, as you see over here. So 1,100 minus 1,000 divided by 100 gives you 1. So what do you know right away about a Z-score of 1? Anybody? What is that telling you? You end up with a Z-score of 1. It's a standardized normal curve. So what does the 1 mean? No one knows? Okay, is everybody asleep while I was talking? Someone tell me what the Z-score means if it's a 1. No one. It means it's at 1 standard deviation above the mean. Remember that? The Z-score is also the standard deviation. When X equals 900, we have 900 minus 1,000, the mean, divided by the standard deviations, the 100 equals minus 1. So what does minus 1 represent? I'm not interested in the skewness. And why are you talking about skewed? There's no skewing here. Okay? What does the number minus 1 represent? I just told you what 1 represented. What does minus 1 represent? Nobody's paying attention. 1 what under the mean song? You have to be specific. It's 1 standard deviation below the mean, not back of 1 standard deviation. It's not 1 under the mean. It is 1 standard deviation below the mean. Okay? Remember, a negative number for the Z-score doesn't necessarily mean it's negative. It means it's below the mean. Okay. All right. So we looked at that. Oh dear. So using the normal curve to approximate binomial distribution problems. I can't read that. Let me see if I can see it. Sorry, I apologize for that. I'm not sure why that is there. Okay, it should be the normal example. 62% of 12th graders, 62% of 12th graders attend school in a particular urban school district. If a sample of 500 12th grade 12th graders are selected, find the probability that at least 290 are actually enrolled in the school. So first you have to determine P, Q, and N. P is defined in the question as 62%, or remember, 0.62. To find Q, you subtract P from 1, and 1 minus 0.62 is 0.38. And N is defined in the question as 500. That's your sample. Step 2, you determine if you can use the normal distribution. N times P equals 310, and n times q equals 190. And what does that add up to? Anybody? 190 plus 310? Hello, anybody out there? What is 190 plus 310? 500, which is, that's our sample, okay? Because these should always add up. We find the mean by multiplying n and p, and p of n times p equals 310, okay? Then we multiply step 3 by q. 310 times 0.38 equals 117.8. We take the square root of step 4 to get the standard deviation, sigma. The square root of 117.8 equals 10.85. The formula for standard deviation for binomial is square root of the n times p times q. You write the problem using correct notation, p of x greater than or equal to 290. Then rewrite the problem using the continuity correction factor p. So x is then or equal to 290 minus 0.5, which equals p of x is greater than or equal to 289.5. Okay? So that is using the normal curve to approximate the binomial distribution, if you have such a problem. Okay? So let me show the video. Okay.
STAT1010.com, and in this video I'm going to show you an example of working a continuity correction factor problem. I have a sample problem here. I've got n equals 20. P, that's the probability, is 0.25. What's the probability x is greater than or equal to 8? Well, the first thing I want to do is figure out n times p. So n times p, I've got n is 20 and p is 0.25. 20 times 0.25 equals 5. And I also want to figure out n times q. Q is just 1 minus p. Well, if my p is 0.25, then my q is 0.75. So n times q is going to be 20 times 0.75. That equals 15. Now the continuity correction factor says that if n times p and n times q are over 5, then we can use the continuity correction. Well, these are both over 5. This right here is also the mean of a binomial probability distribution, n times p. We're going to need that another step, so I'll just make a note of that. Next, I want to figure out the variance. The variance of a binomial distribution is n times p times q. My n is 20 and p is 0.25 and q is 0.75. And if I multiply this through, I get 3.75. So this is my variance. Next, I want to actually use the continuity correction factor. I'm going to consult a chart. You can find this table on our website, statistics.how-to.com. What I'm looking for here is the probability that x is greater than or equal to 8. So if I look here, the probability that x is greater or equal to a number, and I'm going to subtract with continuity correction you're either subtracting or adding. In this case, I want to subtract. So I need to subtract 0.5 from my x value. My x value is greater than or equal to 8. So instead of 8, I'm going to have 7.5. So 8 minus 0.5 is 7.5. I'm going to use this in finding the z value. If you're not very familiar with finding z values, you can check out our other video. The formula is z equals x minus the mean, x bar, all over the standard deviation. My x is now 7.5 because I used that continuity correction factor, 7.5, minus the mean, which we figured up here as being 5. And this is going to be all over the standard deviation, which is the square root of variance. So I'm going to use the variance we found here, 3.75, and take the square root. And if I figure this out on the calculator, I get 1.29. This is my z-score. I'm going to look up the z-score in the z-table. 1.29 gives us an area of 0.9015. My area was 0.9015. Not quite done yet. That's because I need to subtract from 1. Now the z-score here is going to give us the value left of this point, which was 1.29. What we want is this area here, so we're going to need to subtract the score from 1. 1 minus 0.9015 is equal to 0.0985. And this is the area right of that z-score, and this is our probability for x is greater than or equal to 8. Check us out.
Okay. That's basically the correction formula when you're finding the probability. And let me get back to the PowerPoint. Okay. So, as done in the video, you draw a diagram with the mean in the center because you know it's a standardized bell curve. You shade the area that corresponds to the probability you are looking for. So you're looking for, in this case, just to go back, there's a continuity correction factor. You want x greater than or equal to 289.5. All right. So we know the mean. This is where 289.5 resides. So it's to the left of the curve. Everybody agree with that? Okay. So if we want to find out, we're looking for x is greater than, so it's the area to the right that we want to know. Any questions about that? All right. So you find the z-score. So you find this by subtracting the mean from the probability you found in step 7. You can follow this again in step 7. Then dividing by the standard deviation. So 289.5 minus 310 divided by 10.85. The z-score is minus 1.89. Now, when you go to the z-table, you can look this up and it will give you what the area is. So the area for minus 1.819 z-score is 0.4706 or 47.06%. You add 0.5 to your answer. And why do you add 0.5? Can anybody tell me? What's the area of the total curve? What do all probabilities add up to? Not because of the 500. What do all probabilities add up to? 1 or 100%. Okay. So we found this 0.4706 for the z-score of minus 1.819, which is below the mean, right? So we only found that area from minus 1.819 to the mean, which is 0.4706, but we also have to add the additional 0.5, 50%, which is on the right side of the curve. Does everybody understand that? Depending on the question that's asked, you have to use the whole curve. You may not be asked that question. In this particular example, it's asking to find the total area. So you add the 0.5 to the 0.4706, and you get 0.9706. So the probability is 97.06. Okay. Does everybody understand that? Is there any questions? Okay, remember what it's asking you. Determine if you can use the normal distribution. These are both larger than 5. N is defined as the question as 500. Okay, so it's asking you, can you do that? And your solution following the steps is, yes, the probability is 97.06 that you can use it. So is there any questions about that? Get used to looking at the z-score table, the t-table, and some of the questions at the end of chapter 6. I'm not going to give you the homework today. You'll get the homework for after. Because we haven't finished the chapter yet. So there's no questions on that. Okay, we'll move on. So, normal distribution. We want to find probabilities. So here's an example. We did this already. Okay. We'll do it again. The mean weekly income of a shift foreman with a mean of 1,000 and a standard deviation of 100, and what is the likelihood of selecting a foreman whose weekly income is between 1,000 and 1,100? It's a little different. So for x equals 1,000, okay, so it's 1,000 minus 1,000 divided by $100 is 0. And what is 0? And if the z-score is 0, what is that? Hello? It's the mean, correct song. 0. Remember, every standardized normal curve has a mean of 0 and a standard deviation of 1. So for somebody who earns 1,100, 11 minus 1,000 divided by 100 equals 1. And 1 is representative of what? Z-score of 1 is equal to what? What does a z-score of 1 equal? Anyone? Correct. 1 standard deviation above the mean. Try to get into using that language song. Okay? So, this value 1,100, we know, if you look at this, here's the mean. Mean of 0. We know that 50% of the data lies on the left side here, correct? In this case, 1 standard deviation above is representative of 34.13%. Everybody see that? Okay. So, can someone, if you want to guess or you think it's a logical guess, what is the likelihood of selecting a foreman whose weekly income is between $1,000 and $1,100 from this information? No one? All right. So if you refer to the information regarding the weekly income of a shift foreman in the glass industry, the distribution of weekly incomes follows a normal probability distribution with a mean of 1,000 and a standard deviation of $100. Okay? So if we go back here, what's the likelihood of selecting a foreman whose weekly income is between $1,000 and $1,100? No one? What do you have to do here? Yeah, it's not 84, it's 84.13%. Okay, you're adding the 50% that's below the ones that the mean. That's okay, that's all this part here. Plus, this person earns between 1,000 and 1,100. We're adding this 34.13 to the 50 and get 84.13. Does anybody not see that? Everybody sees it? Okay, great. So, oh, wait a second. Okay, I'm going to show you the video on finding the probabilities. Here's our favorite guy again.
To this lesson, here we're going to continue working these problems with the normal distribution, and we have one up here on the board. We see that ACT scores, which is a standardized test, are normally distributed with a mean of 24 point.
Just to let you know, ACT scores are scores that are used in the United States, are given to high school students. They use that for getting people into college and universities in the States. We do not have that score here.
2, that's the mean test score, and a standard deviation of 4.2. So that might be something else that surprises you. These standardized test scores are normally distributed, much like body temperatures and other things. You see how so many different things are normally distributed. You're always going to have a peak where most of your students are kind of clustered, but then you're going to have outliers on both sides. They're going to fall away in the shape of that normal distribution. The question is, what is the probability that a student, a randomly drawn student, scores greater than 31? Greater than 31. So as before, let's write down what we know. The mean is 24.2. Standard deviation is 4.2. So if we wanted to draw, and we almost always do want to draw a quick picture of what's going on here, then we can draw a normal distribution like this. All right, falls off like this. The mean value at this distribution is given at 24.2. Standard deviation is 4.2 points, so 4.2 points above and 4.2 points below the mean. So we want to find what is the probability that the score is greater than 31 for a randomly drawn student. So what we're after is this right here, because it's greater than 31. We're after that shaded area.
Okay, so what's important in this question is that we're looking for the probability, which is basically the area under the curve that's greater than 31. All right, so you already know from the mean, lower than the mean, we already know that's 50%. Okay, so what you want to do is find what is the area between 24.2 and 31, and you're going to add that to 50%. Okay?
All right, so what we want to do is calculate the z-scores, or the z-score of this value that we're interested in. So the z-score is x minus mu, which is the mean, divided by the standard deviation, 31 minus the mean, 24.2, over the standard deviation, which is 4.2. And that gives us a z-score. When you do the subtraction and the division, that gives us a z-score of 1.62. 1.62. So ultimately, what we're tasked with, you can kind of think of it as this z-score corresponds to this number right here. What we're tasked with is finding the probability that a randomly chosen student, so we say random variable x, is greater than 31, randomly chosen from a population of students that have taken the test, right? Which is exactly the same thing as saying, hey, what's the probability of a z-score off that table being greater than 1.62? This is how we translate it from the real world. We're talking about randomly drawn student, our random variable being greater than 31, which is our test score. We translate it into a problem involving z-scores, right? Now, we cannot read areas greater than z off of that table. We have to change it, as we've been doing in the past, to z being less than negative 1.62. We've explained why in the past. And so whenever you look that up, you'll find that the probability...
Whoop. Okay, I'm not sure why it cut off there, but it did.
Hello, welcome to this lesson. Here we're going to continue working these problems with the normal distribution, and we have one up here on the board. We see that
let me just check this.
scores, which is a standardized test, areas greater than z off of that.
Anyways, all right, so what, I don't know why the video cut off. Anyways, so we're finding a z-score that's greater than 1.62. You would go to the table. You would see what the area is under the curve. Okay. That would tell you what the percentage was. With somebody a score of 31, what that probability was of getting greater than 31. I apologize for that. Is there any questions about this? Everybody understand what you're doing. You're finding the probability. You're looking at where your score is, and you're converting it to the z-score. You look in the table under the area. It will tell you what that is comparable to. Remember, you're adding 50% because of the 50% below the mean. All right? Sorry about that. And I'm just trying to get to the right slide here. Okay, we've done that one. All right. Normal approximation to the binomial. So random variables with a binomial distribution. Who can tell me what a binomial distribution is? Anybody? Anybody awake from the last class? Or sorry, the previous class, so that. What's a binomial distribution? What does bi mean? 2, right? So what is a binomial distribution? Remember, how many values can you have in a binomial? Right. Well, 2 conditions. Okay. So random variables with a binomial distribution are known to be discrete. Okay? You cannot have an infinite number of solutions or answers. So this means that there are a countable number of outcomes that can occur in a binomial distribution. Separation between these outcomes. So for instance, a binomial variable can take a value of 3 or 4, but not a number in between 3 and 4. With the discrete character of a binomial distribution, it is somewhat surprising that a continuous random variable can be used to approximate a binomial distribution. And you're saying, and so what? Okay? Because you may be instances where you will have a binomial distribution or a normal distribution, and you want to approximate it to a binomial distribution to make it look like the normal curve. So for many binomial distributions, you can use a normal distribution to approximate binomial probabilities. So this can be seen when looking at n coin tosses and letting x be the number of heads. In this situation, you have a binomial distribution with a probability of success at p equals 0.5. As you increase the number of tosses, you can see that the probability histogram bears greater and greater resemblance to a normal distribution.
Approximation to the binomial distribution. Continuous normal distribution can sometimes be used to approximate the discrete binomial distribution. Why would we want to do this? In the olden days, it was very useful for probability calculations. The binomial formula can be a bit of a pain if it has to be used over and over and over again, and so this normal approximation came in to make lives much easier. These days, the computers can do the calculations for us, so it's not as much of an issue there. But we still use this normal approximation in statistical inference. When we do things a little bit later on, like statistical inference for proportions, we often use this normal approximation. So it's good to know a little bit about it. Now you may recall that the binomial distribution is perfectly symmetric if p is exactly equal to 0.5 and will have some skewness when p is not equal to 0.5. A normal distribution is a symmetric distribution, and so the normal approximation is going to work best when p is close to 0.5, and it's going to work better and better as we get a larger and larger sample size as well. For illustrative purposes, here is the binomial distribution with n is 40 and p is 0.5. And as you may be able to tell, this is a perfectly symmetric distribution in this case. And let's say we were to superimpose a normal curve over this distribution. It looks awfully normal. That's superimposed normal curve.
Okay, there's your magic. Okay? Binomial distribution with an n of 40 and a p of equal to 0.05. Overlay the normal, standard normal distribution, and it looks identical. That's why if there's cases where you have to approximate, and you will not have to do this ever, because you can always do it on the computer. But it's important that you understand the concept of this.
Curve fits pretty well. And we'd see that if we jacked up the sample size even higher and higher and higher, that normal curve would fit better and better. What if we're a little bit closer to the boundary here? Here p is 0.03, which is close to the boundary of 0. And we've got the same value of n, but we see a little bit of skewness. If we were to superimpose a normal curve, it does not fit very well. If we amped up the sample size larger and larger, we'd see that the normal approximation is going to be better and better as that sample size gets larger and larger. But the general idea here, when we get near the boundaries of 0 or 1, we are going to need a larger and larger value of n for that normal approximation to be reasonable. And this idea is
okay, and here's an important point. You can only have so much unless you have unlimited access to a sample. And you've got thousands or hundreds of thousands of sample sizes. You will never get that to look like a normal curve for that particular value.
Summarized in this rough guideline that the normal approximation is reasonable if both n times p is bigger than or equal to 10 and n times 1 minus p is bigger than or equal to 10. And if you play around with that a little bit, you'll see simply that if p is close to 0 or 1, we need a larger value of n in order for the normal approximation to be reasonable. Now, this is just a rough guideline. Sometimes people replace 10 with 5 here, and sometimes they use different rules altogether. So you should consult with your professor or your...
Okay, so for example, when you are going to be doing your case study, right, if you're going to use the data that I provided, you don't have to worry about the sample size. If you're going to use data that you're going to collect, please make sure that your sample size is minimum greater than 10, minimum, because you will get skewed results. Okay, does everybody understand that?
Your textbook to see what rough guideline they are using. Recall that if x is a binomial random variable, then x has a mean of n times p and a variance of n times p times 1 minus p. And what we were just discussing above is that x can be considered approximately normal in certain settings. And so then we can standardize this in the usual way. We can say x minus mu over sigma, using mu from up here and sigma being the square root of sigma squared from here. Then this quantity we're going to call a z. And we're going to call that z because that quantity has approximately the standard normal distribution. So my z is going to be approximately.
Okay, does anybody not understand the connection? You're taking the mu. You're taking the standard deviation, which is the square root of the variance, which is the sigma squared. Okay, you're determining your z value, which is the x, your unknown, minus the mu divided by standard deviation. Okay, it's basically just plugging in the values to approximate the binomial distribution.
Standard normal, normal with a mean of 0 and a variance of 1. Now we're going to use this in probability calculations. Let x be a binomial random variable with n of 75 and p equal to 0.6. What is mu? Well, we know mu is equal to n times p, and that's going to be 75 times 0.6, and that works out to 45. What is sigma squared? N times p times 1 minus p, and that is going to be equal to 75 times 0.6 times 1 minus 0.6, and that works out to 18. And so our standard deviation is simply going to be the square root of 18. Suppose we wanted to use the normal approximation to estimate this probability. We could calculate the exact probability from the binomial distribution using a computer or even by hand if we had to, but we're going to use the normal approximation here. And we're going to say that the probability that x is bigger than or equal to 52, this is going to be approximately the probability that z is bigger than or equal to, we could say 52, minus the mean, 45, we're simply standardizing like normal, divided by the standard deviation, square root of 18. And this is equal to the probability that z takes on a value that's at least as big as 1.645, rounded to 3 decimal places. Then we would go to a computer or our standard normal table. There's 1.645, and we're interested in this area. I'm going to leave that up to you. Verify for yourselves. That's going to be approximately 0.0495. If you use a standard normal table instead of a computer, you might get a rounded version of that, but you should get pretty close to that value. Now compare that with the exact value that we get if we use the binomial formula, which I'm not showing here, but I used a computer to get the exact value based on the binomial distribution, and we get 0.0611. And our value on the normal approximation, well, it's in the ballpark, but it's still a little bit off. But we can improve that approximation with something we call a continuity correction. We are moving from this discrete binomial distribution to this continuous normal distribution. And when we do that, we can improve the approximation with this continuity correction. To illustrate, let's look what's going on here. This is a plot of the binomial distribution with n is 75 and p is 0.6. And the shaded green part is the probability that we're interested in, the probability that we get a value of 52 or greater. What if I superimpose the normal curve? Here's the superimposed normal curve. And this red shaded area is the probability calculation that we carried out on the last page. And here is the value 52. Now, in the binomial setting, 52 means something. 52 successes out of 75. But on the continuous front, for a continuous random variable, 52 means 52.000000000, infinite zeros there. And it is distinctly different from 52.0000001, say. Now I've blown this part up on the next slide just to make it a little easier to see. So to come closer to regaining our original meaning of 52, we're going to say, okay, 52 in the discrete sense had some meaning. 52 in the continuous sense means exactly 52, 52.00000. So to regain that original meaning, we should let 52 take on all values between 52.5 and 51.5. That way, it comes closer to representing what is intended here in the binomial distribution. And so as we can see here, right at 52, when we started at 52.0000 and we did our probability calculation, we were really missing out an important part. We were missing out this half of 52 in a sense. And so what we really should do is start at 51.5. That's where we should start. So that's what it looks like on the next page. If I start at 51.5, by approximation, my red shaded area here is going to be a lot closer to the total of those green probabilities and a lot closer to reality. So if I want my probability that x is bigger than or equal to 52, before doing the normal approximation, I am going to use the continuity correction and say this is the probability that z is bigger than or equal to 51.5 minus the mean over the standard deviation. This works out to the probability that z is bigger than or to 1.532, and we go to our standard normal table or a computer or what have you, and if we did this without any round off error and just rounded our final answer to 4 decimal places, we'd see that this is 0.0628. And as I'll illustrate in a little bit, that's closer to the true probability based on the binomial distribution than when we didn't use the continuity correction. In this new question, we're interested in the probability that x is strictly greater than 52. That is what the shaded green bits represent. And to be strictly greater than 52, I want to make sure I don't include any of 52, so I really should start right here. I should start at 52.5. Let's see what that shaded area under the normal curve looks like. That looks a little bit better. And so I want my probability that x is strictly greater than 52. This is going to be approximately the probability that z is greater than 52.5 minus my mu, which is 45, divided by the standard.
Is there any questions about the logic that he's using to solve the problem? Everybody understand why he's going to the 0.5? It's to get closer to the binomial exact number, because this is using an approximation using the normal distribution. Any questions about this? Or everybody's okay with this? All right, no questions? Okay, all right. Continue.
Deviation, which is the square root of 18. This works out to the probability that z is greater than 1.768. If we found that value under our standard normal curve, 1.768, and we did it without any round off error and rounded our final answer to 4 decimal places, we would see that's the answer. And you should be able to come close to that, not exactly that, from a standard normal table. What about here? Let's say I wanted the probability that x is less than or equal to 52. That's what that shaded green bit represents. And I can't start exactly at 52. That wouldn't be quite right. To include all of 52 and go left, I need to start here. I need to start at 52.5. So let's see what that looks like when shaded under the normal curve. That looks like it might provide us a pretty reasonable approximation. So when I want the probability that x is less than or equal to 52, that's going to be approximately, with my continuity correction, I want to include all of 52, and so I should start at 52.5. Subtract the mean, which is 45, and divide by the standard deviation. This is going to be equal to the probability that z is less than or equal to 1.768. If we plot that out, 1.768. That's this entire area here. And that works out to 0.9615. What about if we're interested in the probability that x is strictly less than 52, which is represented by the green shaded bit? If I'm going strictly less, if I don't want to include 52, then I should start here at 51.5. Let's see what that looks like when shaded in. That looks like that might give us a pretty darn reasonable approximation. So if I want my probability that x is less than 52, then I'm going to say that's approximately the probability that z is less than 51.5 minus mu over sigma. And this is equal to the probability that z is less than 1.532. And if we put that into our computer, and we did this without any round off error, and then just rounded to 4 decimal places at the bitter end, we would say that this is 0.9372. So let's look at a summary of what we just did. If I want the probability that x is bigger than or equal to 52, then I want to include all of 52 and go right, which means I should start at 51.5. If I want the probability that x is strictly greater than 52, well, I'm going right, but I don't want to include any of 52, so I should start at 52.5. If I am going left, less than or equal to 52, I want to include all of 52 while going left, which means that I should start at 52.5. And if I'm going strictly less than 52, I want to make sure I don't include any of 52 while going left, which means I should start at 51.5. My strong.
Okay, so is there any questions about this? So when you are doing the normal approximation, and depending on what probability you have to find, if it's greater than, okay, in this case greater than or equal to 52, you're going to start from 51.5. If it's just greater than 52, you're going to start at 52.5. Less than or equal to 52, you're going to start at 52.5. And less than 52, you're going to start at 51.5. Is there any questions about that? Does everybody get that logic? Because that's what you're doing to adjust your approximation, because you're using standard normal distribution. Yes? Okay, great.
Strongly recommend that you don't simply memorize this, but that you try to follow the underlying. If you truly understand why we're doing what we're doing here, it'll be easier to do properly when you have to. Now let's take a quick look here at how that continuity correction improved the approximation for a couple of cases that we just looked at. If we're interested in the probability that x is bigger than or equal to 52, without the continuity correction, we got 0.0495. But with the continuity correction, we got 0.0628, which is much closer to the exact value based on the binomial distribution. That's what this exact value is coming from. Similarly, down here, when we wanted greater than 52, we had 0.0495. We used the same calculation in both cases. We didn't use our continuity correction. And with the continuity correction, we get 0.0385, which is much closer to the exact value based on the binomial distribution. So the continuity correction has greatly improved our approximation.
Okay. We'll go back to the slides. All right. Okay, so we're here. So every normal distribution is completely defined by two real numbers. These numbers are the mean, which measures the center, and the standard deviation, which measures the spread. For a given binomial situation, you need to be able to determine which normal distribution to use. Selection of the correct distribution is determined by the number of trials n in the binomial setting and the constant probability of success p for each of the trials. The normal approximation for the binomial variable is a mean of n times p and a standard deviation of np times 1 minus p times 0.5. That's where he got that extra 0.5 from. So for example, suppose that you guessed on each of the 100 questions of a multiple choice test, where each question had one correct answer out of 4 choices. The number of correct answers is a binomial random variable because it's either correct or it's incorrect. N equals 100 and p equals 0.25. Thus, the random variable has a mean of 100 times 0.25 equals 25, and a standard deviation of 100 times 0.25 times 0.75 times 0.5 equals 4.33. So a normal distribution with mean 25 and a standard deviation of 4.33 will work to approximate this normal distribution. Remember, you're adding the 0.5, okay, to get it close enough to the binomial distribution. So when is using the approximation appropriate? By using some math, it can be shown that there are a few conditions that you need to use a normal approximation to binomial distribution. The number of observations must be large enough and the value of p so that both n times p and n times 1 minus p are greater than or equal to 10. This is a rule of thumb, which is guided by statistical practice. And that's why I say when your sample size should be greater than 10, that's close. You're going to use your own data, but it's better to use the data I supplied. But if you want to use your data, make sure your sample size is greater than 10, and basically much greater than 10. So the normal approximation can always be used, but if the conditions are not met, then the approximation may not be that good approximation. So for example, if n equals 100 and p equals 0.25, then you are justified in using a normal approximation. Your sample is 100. This is because np equals 25 and n times 1 minus p equals 75. Since both of these numbers are greater than 10, the approximate normal distribution will do a fairly good job of estimating binomial probabilities. And why do you use it? No, some people don't know, some people don't care. But you're calculating by using a very straightforward formula to find the binomial coefficient, which, as explained in the video, takes a very long time to figure out manually. Unfortunately, due to the factorials in the formula, it can be very easy to run into computational difficulties with the binomial formula. The normal approximation allows us to bypass any of these problems by working with a familiar friend, the table of values of a standard normal distribution, the Z table. So many times, the determination of a probability that a binomial random variable falls within the range of values is tedious to calculate. This is because to find the probability that a binomial variable x is greater than 3 and less than 10, you would need to find the probability that x equals 4, 5, 7, 8, and 9, and then add all of these probabilities together. If the normal approximation can be used, you will instead need to determine the score corresponding to 3 and 10, and then use a z-score table of probabilities with a standard normal distribution. Because what is the Z table showing you? It's showing the area under the curve, which represents probability. Any questions about that? Okay. So, the normal distribution, which is a continuous distribution, yields a good approximation of the binomial distribution for large values of n. So, the normal probability distribution is generally a good approximation to the binomial distribution when n, well, we know are both greater than 5. I don't know why I've got those characters there. This is because as n increases, the binomial distribution gets closer and closer to the normal distribution. So here we have binomial distributions of n of 1, 3, and 20. Okay, where I believe that's supposed to be the variance equals 0.5. So if you look at the first graph here, that doesn't really tell you anything. They both look the same. With an n of 3, there's a tiny, tiny bit. Maybe it looks like a curve. But when you have an n of 20, it starts looking like a normal curve. And that's why you want to increase your n in a possible binomial distribution. And that's another thing for your case study. Try to make sure it's not a binomial distribution, or else you may end up with a lot of problems because your sample size should be very large. Okay, so we looked at this a bit, the continuity correction factor, value 0.5, subtracted or added depending on the problem to a selected value when a binomial probability distribution, again, a discrete probability distribution, is being approximated by a continuous probability distribution. So one of 4 cases may arise. The probability at least x occurs, use the area above x minus 0.5. The probability that more than x occurs, use the area above x plus 0.5. This is similar to the video. The probability that x or fewer occurs, you use the area below x minus 0.5. And for the probability that fewer than x occurs, you use the area below x plus 0.5, which was shown in the video. Okay, and I've got another video on this. I just want to show you again with the continuity correction factor. And
From statisticshowto.com, and in this video I'm going to show you an example of working a continuity correction factor problem. I have a sample problem here. I've got n equals 20. That's the probability.
Oh, sorry, I showed this one already to you. I apologize. Okay, I put it in the wrong spot. But anyways, are there questions about the continuity factor? Remember, you use it when you're approximating a binomial distribution, which in real life is probably never going to happen unless you work for a company that's flipping coins. Okay, here's an example of the normal approximation to the binomial. So suppose the management of the Santoni Pizza restaurant found that 70% of its new customers returned for another meal. For a week in which 80 new first-time customers dined at Santoni's, what is the probability that 60 or more will return for another meal? So step 1, find the mean and the variance of a binomial distribution and find the z-score corresponding to an x of 59.5. X minus 0.5 is the correction factor. And step 2, determine the area from 59.5 and beyond. All right, so first we have to find the mean and the variance. Use the mean equals 80 times 0.7 equals 56. The variance is 80. Okay, that's your first time customers. Times 0.7, that's 70%. Times 1 minus 0.70 equals 16.8. Standard deviation, square root of the variance, 16.8 equals 4.10. Substituted in the Z formula, x minus mu over sigma is 59.5 minus 6 divided by 4.10 equals 0.85. Okay? So if we look at the chart here, 56 is our mean from up here. Okay? Standard deviation is 4.10. We want to know, find the z corresponding to an x of 59.5. Okay, 59.5 is here. Okay, this is, the z score is 0.85 standard deviations away from the mean. Any questions about that? You understand why this is equivalent 0.85 to the standard deviations, 0.85 standard deviation. Okay? So the area, and when you do this, you look at the z-score table. It will give you the area. When you have the z-score, it will tell you that the probability is 0.1977 or 19.77%, that 60 or more out of the 80 will return to Santoni's. Is there any questions about that example? No questions? All right. Okay. All right, we'll try this one and we'll see. All right, talking about an exponential distribution. And what is it? The exponential distribution, also called the negative exponential distribution, is a probability distribution that describes time between events in a Poisson process. There is a strong relationship between the Poisson distribution and the exponential distribution. So for example, let's say a Poisson distribution models a number of births in a given time period. The time in between each birth can be modeled with an exponential distribution. And that's an example of the curve is exponential. Okay? Moves in an exponential function. So I will show you the video of that. Okay, this is a long video, but I'm not going to show the whole video. Maybe I will, we'll see.
To look at the exponential distribution. So the exponential distribution may be used to answer the following questions. How much time will elapse before an earthquake occurs in a given region? How long do we need to wait before a customer enters a shop? How long will it take before a call center receives the next phone call? And how long will a piece of machinery work without breaking down?
Okay, let me just ask a question of everybody. Are these important questions to ask? Is everybody still awake? Okay, Song, why are these important? And why does it depend, John? Tell me why these are important questions to ask. And why does it depend, John? If you live in an earthquake region, wouldn't it be good to know? You can get precise data or as close as possible, right? Because these are real problems. If somebody owns a business, they might want to know how long it takes before a customer comes in. Yes? No? Yes. And if you have a call center, don't you want to know how long it takes before a call center receives a phone call? Is that important? And if you own a manufacturing plant, let's say you're building cars, How long will a piece of machinery work without breaking down? Is that important? No. I understand. You have to collect data. But if it's in a known, if you're living in a known earthquake region, wouldn't it be good to know approximately when an earthquake would hit? Yes. Okay, so these are real world situations.
Now, in those four questions, time is the common is the commonality between all four of those. It doesn't actually the exponential distribution is not only for time, but it's the easiest point to start at for the exponential distribution we'll use for the time being. So let's move on. Just as a quick remark, time is a continuous variable. So that is why the exponential distribution will be a continuous probability distribution. So all of these equations concern the time we need to wait before a given event occurs. And if this waiting time is unknown, it is often appropriate to think of it as a random variable having an exponential distribution. Time x, we're going to call our variable x, our waiting time or our time without breaking, whatever. We're going to call that x from now on. The time we need to wait before the event occurs has an exponential distribution if the probability that the event occurs during a given time is proportional to the length of the time period. That is something that is actually going to come up as being very important later on. I'll just indicate that with an arrow there. That's actually quite an important statement here. Maybe not so obvious now, but it will be later. So the probability density function of the exponential distribution is given as follows. So x is some time period. This is like some value of some realization, for example, 2 years or 10 seconds or something.
And no, you do not have to memorize this function, okay?
Lambda is this thing called the rate parameter. We're going to see a lot of it later on. And it is the inverse of the expected duration. So we could sort of say mu equals 1 over lambda, or lambda equals 1 over mu. Both of those are actually equivalent to one another. I'm actually going to call this the expected value instead, but it actually is called mu. Also, I'm just going to stick with the expected value of x later on. Now, we cannot have a negative period of time. Okay, you can't wait less than 5 seconds. So really, that is why we have a 0 here. If we have a negative time period, the probability of that is 0 because that is an impossible event. So it's the top line we're going to look at. So lambda times e to the power of minus lambda x. Okay. So again, the key thing to pick up on here is the rate parameter. Now, if the expected duration is 5, let's say for example 5 seconds, then the rate parameter is 0.2. The reason I mentioned that actually is because that is the way the information might be given in an exam question. You might be given the expected value and asked to determine the rate parameter. So it is 0.2 if the expected duration is 5. Now, what is the expected duration? It is the amount of time you expect to wait, or the amount of time you expect to wait before a new customer will call the telephone center, or the amount of time you expect the machine to operate without breaking down. That's the expected duration. So, let's move on. So this is a bit more relevant to what we're going to do with the cumulative density function here, the CDF. And the cumulative density function is given as follows. So again, for some time period x, the probability of the duration less than that is equal to 1 minus e to the power of minus lambda x. And again, we can't have negative time periods, so that's why we have a 0 here. Okay, so this is the formal definition here, but this is actually the second equation I hear is a bit easier to work with for pen calculation. So this is the one you'd have to remember. And actually, it's not actually given in a lot of exam papers because it actually is quite easy to remember. So, for example, suppose lambda is 0.3, and suppose that x is equal to 10. What we might do is sort of say probability of x less than or equal to 10 equals 1 minus, multiply those two terms out, we get e minus 3, something like that. And then we can just work it out on a calculator. So the probability of x less than 10 is, we just work on the calculator and solve that. We're going to do a bit of that later on, so I'm not going to do it now. So moving on, this two important matters. The expected value of the random variable x is given as follows. I mentioned this earlier on as mu, but use e of x from now on, the expected value of x. The variance of an exponential random variable is also v of x, which is 1 over lambda squared. Actually, another way is you can figure that out quickly, is just consider it a mu squared. The expected value of x squared. So that's actually quite easy to remember in this case. So let's move on. We have an example here now. Assume that the length of a phone call in minutes is an exponential random variable with a rate parameter of 1 by 10, 1/10, 0.1. So if someone arrives at a phone booth just before you arrive, find the probability that you have to wait less than 5 minutes, greater than 5 minutes, and between 5 minutes and 10 minutes. So, and also compute the expected value and variance. I'm actually going to change that to 10 minutes just to make that a little bit easier to work with, because I'm actually going to just to speed things up. So let's move on. So let's do the first one. So compute the probability of x less than or equal to 5 when the rate parameter lambda is 1/10. Now I included the equation that we're going to use. So let's first off put in our values here. The probability of x less than or equal to 5 equals 1 minus e by minus 5 over 1/10. That's 1 minus e 5 over 10. That's equal to 1 minus e minus 0.5. So this is where we get out our calculators. And that is equal to, 1 minus 0.6066. I'm just going to write to the 4 decimal places. You might get values slightly different to that. And then the answer is therefore, I'm going to write this in 0.3934. Okay. So you might get a value slightly different to that. It just depends on the way you round it. It should be around 30%, 0.3934. So that's the answer to the first one. So let's move on to the second one here. I've actually changed it a bit. Sorry, first off, that is the a sort of easier version of what I've just written in the last slide. Again, a little bit of rounding error comes into play. So this is actually 0.6065 with a few extra numbers there, but then I just rounded it to 4 decimal places. So that's how we would calculate that. And again, it's a bit easier to read. So if you want to sort of pause and just set down, that's a good time to do it. So let's move on to the next one. So compute the probability of x greater than or equal to 10 when lambda equals 1 divided by 10. Now, this is what we first important point here to pick up on. That is greater than or equal to 10. That's the complement. So what we're going to do is apply the complement rule here. Okay. So the probability of x greater than or equal to small x, the time period greater than or equals x, is the complement of this. So we have 1 minus this here. Now, let's just see how did I get to here. This is the actual equation we're going to use. It's actually very simple. So essentially, this is 1 minus e to the lambda x and what we're going to do is go 1 minus that. The 1's cancel out. 1 minus 1 is just 0. And that minus there and that minus there just gives us a plus. So again, it's straightforward complementary. So this equation here, this term here, is the one we're going to use. So it's actually quite easy. So what is it? Well, we have x, small x is 10 and lambda is 1/10. So probability of x greater than or equal to 10 is equal to e to the minus 10, or 10, which is e minus 1. And working that out on a calculator, we get 0.3678. So that's the answer to the second one there. So the probability of x greater than or equal to 10 is that there, 0.3678. So again, on the next slide, I have it written a bit neater. Read that there. Pause it if you want to pause it. So again, that's 10 multiplied by 1 over 10, which is 10 over 10, and also minus sign. Okay, so that's the answer there. So let's move on to the last part. What is the probability of x between 5 and 10? So this is where you would use the sort of interval rule approach, or the interval approach. So the probability of being inside the interval, okay, is the complement of being outside the interval, okay? So the probability of being inside the interval is the 1 minus the probability of being outside the interval. So it's very stands to reason. So this approach here is.
So just remember when he's talking about complement, going back to the probability, you know, it's in or it's 1 minus because it adds up to 100%. Okay?
The interval approach, and it is really handy when you do these questions. So probability of being outside the interval is the composite event, or the joint event, of being too low for the interval, probability of x less than or equal to 5, or being too high for the interval. There's a typo there. It's actually should be x greater than 10. So this is too low here, and this is too high here, and together are the outside the interval, and this is probability of being inside the interval, and we have this 1 minus term here. So that's the complement rule. So what all we have to do is add the probability of being too low to the probability of being too high. That gives us the probability of being outside, and then just find the complement of that. So the probability of being too low, probability of x less than or equal to 5, was 0.3934. Again, that's something we've done earlier. The probability of being high, probability of x greater than or equal to 10, that is 0.3678. So the probability of being outside is just add those two numbers together. And so it's 0.3934 plus 0.3678. And then we get our answer there, that's 0.712. Again, you might get slightly different numbers just depending on how well you rounded it on the calculator. So the probability of being inside the interval is the complement of that. And so the answer is 0.2388, so about 23%. So that is the answer to the part C. We have one more job left, that is to compute the expected value and the variance. So the expected value of the variable is 1 divided by 1/10. That is just simply 10. Again, something I actually mentioned earlier. So that is equal to mu. Okay, and that's equal to mu squared. That's the expected value squared. So that's actually quite easy to do in this particular instance. So that would actually be 10 minutes properly, and that's 10 minutes, or 100 minutes squared. It actually would sort of say 10 minutes, a standard deviation of 10 minutes. Okay, that ends our presentation.
Okay, thank you for watching. Just wanted to get the major points of what was happening with an exponential distribution. I'm going to stop there, but what I'd like to do is to what would I like to do here? Just quickly go over the assignment for handing in the research proposal. And let's see. Unfortunately, it looks like I cannot show that. I'm not sure why. No, can't show it. But what I'd like you to do is if people, okay, and remember to go into the website and find the research proposal. And what you want to do is we want to answer the questions. And that's what you're handing in. Okay? I'm looking at business research methods proposal outline, which is in the research proposal. You're going to look at the data. Remember, anybody that's going to collect their own data has to go through me so I can see what the data is and have to approve that and go ahead. But in your proposal, you want a title. I don't know if people have written research papers before, but this is the sort of similar format. The title of your research, the purpose of the search, okay? You want to come up with something about the data, some research questions, okay? Minimum 3 about the particular data. You know, what is it that, so I'm looking at the example here and it's like, are sport and recreation majors in favor of a new rec center being built on campus at Keystone College? You know, is the exercise equipment satisfactory? Would an improved athletic facility draw more prospective students to enroll at Keystone College? So you look at the data, look at the variables, and look at what questions you can answer from that data. Now, the next section is supporting literature. If you can find some articles, if you can find at maximum 3 articles, has to do with the data, that would be great. If you can't find anything, let me know. All right. And the research methodology is if you're using the data that's already supplied to you, is, you know, what are you going to do? But the questions, the assignment already has what you're going to do, and it's kind of repetitive. But if you can just put that in, and what kind of data analysis you're going to do, and your population and your sample size. So my question is, so this is due next week or from today till next Friday. You know, the whole assignment is worth 20%. This is worth 5%. The research paper is worth 15%. If you don't get it into me by next Friday, then that part will be deducted. Now, is there any questions about the research proposal, the research paper, anything like that? Everybody understands what they have to do? Yeah, Brenda. Yes, you can do it in pairs, John. If somebody wants to do it with you, that's fine. Just let me know, but I still need a research proposal from both of you. can be exactly the same, but I need it from both of you. All right, I'm going to send out another announcement probably on Sunday or Monday, just repeating what I just said for the people that obviously were not here. And so if everybody is understanding about that, have a good intersession week. Hopefully you don't have too many assignments like this one. And I will also send out, remind you that remember when you're back, you will have the test on chapter 5. We will probably finish chapter 6 on Tuesday of the week after the intersession. So the test will probably be Friday. And than that, everybody have a good break, and hopefully we'll have some nice weather. Okay? Thank you. See you in a couple of weeks.